Our last class we discussed flow through the pipes. Okay, if it is flow through the pipe, how the velocity distribution and the temperature distribution inside the pipe we discussed. So which is two different cases. One is to be a duct or pipe is maintained at a constant wall temperature, or it is subject to constant heat flux. Okay. So here just there is a flow through the pipe is called as a internal flow. Okay, so this internal flow we calculate properties are to be evaluated at a bulk mean temperature. This mean with Tm, I used Tb is a bulk mean temperature is equal to inlet temperature of the fluid plus your outlet temperature of the fluid divided by 2. So we are using this relation, we have to calculate your properties. Okay, the properties could be evaluated at a bulk mean temperature. So suppose if it is considered a duct, if the flow is going inside, suppose a water is flowing through the pipes at the initial temperature Ti, the duct is the pipe is maintained at a constant wall temperature Tw. Okay, here the Tw is greater than Ti means the heat is transferred from the pipe to fluid. Therefore, your exit of temperature of the fluid will be greater than your inlet temperature but less than your wall temperature. This that your exit temperature of the fluid is to be To. Then your bulk mean temperature is nothing but your average temperature of your inlet average sum of average temperature of inlet plus your outlet temperature of the fluid. Therefore, Tmi plus Tmo divided by 2 is nothing but your inlet and outlet temperature of your fluid. So the properties to be evaluated at a bulk temperature. So in case of if it is a flow or a flat plate, the flow takes place laminar to turbulent zone. But in this case, the flow is only this flow is passes to the confined passage. Therefore, maybe it is entering, maybe laminar, maybe turbulent. There both the flow will be not possible in the single case. Okay. So depends upon the Reynolds number, we classified flow to the pipes, the laminar flow and the turbulent flow. If the Reynolds number is less than 2300, we are considered to be a laminar flow. Okay. So in this case, we have to discuss two different constant is to be a heat flux to the system. Okay, so there are two different regions there. One is to be a entry region or a thermal boundary layer region, as well as your fully developed flow. So if it is we consider say entry region, in this region your hydrodynamic layer fully developed, this is a starting stage of your thermal layer developing. So while occurring this situation, we have to use your Nusselt number formula is equal to 3.66 plus 0.0668 d by L into Reynolds number at a diameter d, Prandtl number divided by 1 plus 0.04 d by L, Reynolds number at a diameter, Prandtl number whole power 0.67. Okay, so this case of Prandtl number is greater than 0.7. This we consider the pipe is to be smooth pipe and also constant wall temperature. Use this formula, we can find out your Nusselt number. Okay, suppose the pipe length is to be a short length. While calculating the ratio of x by d divided by Reynolds number at d Prandtl number, this value is less than 0.01. Then we can use this relation number to find out your Nusselt number. Once if you know the Nusselt number, the Nusselt number is equal to HD by K. We are using this relation, we find out your convective heat transfer coefficient. Again, it is a maintained a constant wall temperature. You see that in your previous case, this the hydrodynamic boundary layer is fully developed, but the starting stage of your thermal layer developing. So this equation as well as this equation we are using more or less we are getting similar result only, slight deviation only is there. So we can precisely we can pick whether it is a fully developed hydrodynamic layer means we can use this equation or your previous equations. And also this fully developed your thermal layer. If it is a plate is pipe is maintained at a constant wall temperature, this flow is a fully developed thermal layer means we have to use Nusselt number is equal to 3.66. Okay. So simultaneously development of hydrodynamic and thermal layer. Both the layers is fully developed. Then we can use this formula. Nusselt number is equal to 3.66 plus 0.104 Reynolds number D Prandtl number D by X divided by 1 plus 0.16 into Reynolds number D Prandtl number dot D by X by whole power 0.8. Okay, we can this above expression used for liquids case. Okay. These all are formula available in your data book. So once you read the problem, then what kind of problem what kind of situation they gave, based on that you have to select one formula to find out your Nusselt number. Then after you find out your convective heat transfer coefficients. In case of the flow is to be turbulent, it means Reynolds number is greater than 2300. These will be find out your friction factors. Okay, and if it is a smooth pipe, we can use this formula to find out friction factor. If they will ask find out the friction factor, we have to use rough pipes. We use these conditions. Okay, then this is for entering regions. If the turbulent blows, turbulent flow at the entering region, we can use this formula to find out your Nusselt number. If it is a short pipe, then we can use this Nusselt number. This most of the case we are assuming the flow is a fully developed flow. Therefore, your Nusselt number is equal to 0.023. Reynolds number at a diameter D is 0.8 into Prandtl number whole power n. Here n is will be 0.4 for heating of fluids. Okay, suppose n equal to 0.3 for cooling of fluids. So what is mean by n equal to 0.4 and n equal to 0.3 means, suppose if we consider say a duct or pipe, though water is flowing through the pipe, so the inlet temperature is having some temperature Ti, then your out this maybe this maintained a constant wall temperature, then the heat will, if you the wall is temperature Tw, if W greater, heat is transferred from the pipe to fluid. Therefore, your outlet temperature of the fluid is to be higher than your inlet temperature, but less than your wall temperature. Okay. Therefore, in this case, the fluid is heated while passing through the pipes. Therefore, we are using n equal to 0.4. Okay. Suppose if the duct is maintained at some temperature, while the inlet fluid is having higher than the duct pipe wall temperature, therefore the heat is transferred from the fluid to your pipe. Then in this case, your inlet temperature of the Ti is greater than your To, then in this case the fluid is cooled. Then we can use n equal to 0.3 for cooling of fluids. Okay. So these all are formula available in your data book. Based on that, we solve some numerical problem. We try to solve some numerical problem. Which type of equation is suitable for that one? Okay, we have to select. So here, problem number 3.12. Water at bulk mean temperature 40 degrees Celsius flow through the tube of 0.05 meter inner diameter with a velocity 0.025 meter per second. The tube is 2 meter long and its surface is at a constant temperature of 60 degree Celsius. Okay. Determine the heat transfer and the mean temperature rise during the flow, assuming hydrodynamic boundary layer already developed. So we consider the pipe is the flow through the pipe. Okay, some water is flowing through the pipe. The inlet temperature of the pipe is Ti. Then your outlet temperature of the fluid is to be To. Okay. Then this duct is maintained at a wall temperature Tw is given. The duct is maintained at a temperature of, this is maintained at a 60 degree Celsius. So 60 degree Celsius. Okay. So in this case, the inlet temperature of fluid and as well as outer temperature of fluid is are unknown. But even though they will give the bulk mean temperature. So the where properties of fluid is to be taken as a bulk mean temperature. Bulk mean temperature is nothing but TB. The TB equal to bulk mean temperature dP is equal to your inlet fluid temperature Ti plus TO outlet temperature P divided by 2. So in this case, inlet and outlet temperature is not given. Anyway, they will give your bulk mean temperature. So TB directly given. So it should be a 40 degrees Celsius is given. Okay. Therefore, the properties of fluid is taken at 40 degrees Celsius. Here the fluid used to be a water. Therefore, the properties of water at 40 degrees Celsius are, you can refer data book. We find out these following properties. So density of the water at 40 degrees Celsius is rho is equal to 995 kg per meter cube. Then your kinematic viscosity is 0.657 into 10 power minus 6 meters per second. Then your Prandtl number is to be 4.34. Then your specific heat Cp is equal to 4178 joule per kg Kelvin. Then thermal conductivity K is equal to 0.628 watt per meter Kelvin. Okay. So we are assuming, first of all, once we take the property, then we have to this type, whether it is to be a laminar flow or to be a turbulent flow. Okay. Then we have to find out the Reynolds number. What is the formula for Reynolds number? Reynolds number is equal to velocity ud divided by your kinematic viscosity. So here, what is your velocity? Velocity of the flow is 0.025. It is for u. Then what is your diameter of the pipe? Diameter of the pipe is 0.05. Therefore, ud divided by your kinematic viscosity. The kinematic viscosity is 0.657 into 10 power minus 6. While using this formula, I find out my Reynolds number. Reynolds number is equal to 1902.6. Therefore, it is less than 3300. Therefore, we are assuming the flow is to be a laminar flow. Okay. The first, once you know that flow, which type of flow, laminar flow, then this case also they will given a assume a hydrodynamic boundary layer, all fully developed. So we just to go to a data book. The flow is to be a laminar flow. Okay. Then it is a hydrodynamic layer is fully developed. So from this equation, I took your Nusselt number formula is equal to 3.66 plus the whole things into 0.0668 d by L, Reynolds number at a diameter d, Prandtl number divided by 1 plus 0.04 into T by L, Reynolds number at a d, Prandtl number for 0.67. We can use this relation also, or otherwise, if it is a pipe should be a short length, then we can use this relation. This formula also suitable for fully developed hydrodynamic boundary layer, while it is maintained at a constant wall temperature. Okay. We have to find out this ratio x by d divided by Reynolds number d in Prandtl number. This value is less than 0.01. Then we can use this relation also. Okay. So here I used both relation, but it's very simple. Here assume a hydrodynamic boundary layer is already developed. Therefore, find out a ratio x by d Reynolds number at Prandtl number. So here x, what is your the tube length is to be 2 meter long. Therefore, 2 divided by d diameter is 0.05 divided by your Reynolds number at a diameter is a 1902.6 into Prandtl number 4.34. We just to find out this value, ratio of this value is less than 0.01. Therefore, I am using this relation to find out your Nusselt number. Nusselt number is equal to 1.67 into Reynolds number, Prandtl number, then d by x whole power 1 by 3. 1.67. Your Reynolds number is to be 1902.6. Your Prandtl number is to be 4.34 into diameter is 0.05 divided by 2, the whole power 1 by 3. We are getting Nusselt numbers equal to 9.86. The same way, on another one more relation is there, that will be a fully developed hydrodynamic boundary layer. That relation also we are using Nusselt number is equal to 3.66 plus 0.668 Reynolds number, Prandtl number d by x divided by 1 plus 0.04 into Reynolds number, Prandtl number d by x whole power 0.67. So we are using this relation, we find out Nusselt number 9.35, here 9.86. Almost it is a similar value. Therefore, we can use any one of these formula, okay, for fully developed hydrodynamic boundary layer. While using before that, we check the value is the ratio x by t Reynolds number Prandtl number is less than 0.01. Then only this expression is valid. This expression is almost valid for all cases for fully developed hydrodynamic boundary layer. Okay, once you know the Nusselt number, the question is determine the heat transfer and mean temperature rise. So if you want to find out your heat transfer, you know the convective heat transfer coefficient, then we can find out your heat. Okay, then if you know the Nusselt number, what is the formula for Nusselt number? Nusselt number is equal to hd divided by k. This in this case is h is called as your average Nusselt number. So average Nusselt number, h is a convective heat transfer coefficient. Average convective heat transfer coefficient. So h bar equal to n into k divided by d. The Nusselt number we already find out the previous case 9.35 into your thermal conductivity 0.628 divided by diameter 0.05. Okay, so from that we find out your convective heat transfer coefficient is equal to 117.436 watt per meter square Kelvin. Then what is the formula for heat transferred? Then Q is equal to HA into TW minus TB. So in this case, this flow through the pipe. Okay, this flow is inside, it will come out outside. So this inlet temperature Ti, then it is your outlet temperature To, but this wall is maintained at a constant wall temperature Tw. Okay. Then when the fluid flowing through this pipe, the heat is come out from the pipe to your fluid. Therefore, each and every location your Ti inlet temperature keep on increases, that will reach your outlet temperature. That outlet temperature, inlet temperature, but temperature. Therefore, I am taking the heat transfer from this look here. We take your bulk mean temperature. Bulk mean temperature nothing but we have to consider to be a average temperature of inlet fluid plus outlet fluid temperature divided by 2. Therefore, your Q is equal to HA, the TW minus, I am taking TB. The TB is to be your bulk mean temperature. Bulk mean temperature is nothing but average temperature of your inlet fluid temperature plus your outlet fluid temperature. Okay, then we are getting Q is equal to H converting heat transfer coefficient we already find out into area. So this will be, then your Q is equal to H into TW minus TB. So from that equation, we H is a 117.046 area. The fluid will be contact with your pipe. These were circumference into your length. That means pi into d into length will be 2-meter pipe. Therefore, into TW 60 minus 40, your bulk mean temperature. So we are getting Q is equal to 737.87 watt. So once if you know the convective heat transfer coefficient, heat transfer, then one more relation is equal to this Q is equal to nothing but mCp into T naught minus Ti. Therefore, this heat is transferred from this pipe surface to your fluid. That will be convection heat transfer. Anyway, the energy will be added to the heat energy will be added to the fluid. That will be calculated from Q is equal to mCp T naught minus Ti. Okay, this T naught is the outlet temperature of the fluid minus your inlet temperature of the fluid. How much amount of heat lost from the pipe surface, it will go to heat gained by the fluid. The heat gained by the fluid, Q can be calculated, Q is equal to mCp, outlet temperature of your fluid, minus your inlet temperature of your fluid. This T naught minus Ti is called as your temperature rise. From this relation, I find out your Q value, Q is equal to 737.87. Okay, divide by mCp. M is to be your mass flow rate of fluid. That mass flow rate of fluid is will be, we know this equation m dot equal to rho into a into velocity of the flow. Then m dot into density is given 995 kg per meter cube. Here rho is to be, we are calculating the flow is passing through this pipe. So while calculating mass flow rate, we have to take cross section area, cross section 4 in diameter 0.05 square into velocity 0.025. From that, find out mass flow rate. That mass flow rate I am substituting here into your Cp. Cp is a specific heat of the fluid is already given. Okay. Then we have to find out your temperature rise. T naught minus T is equal to 3.61 degree Celsius. Okay. Then we are move on. In these problems, they will ask only the temperature rise as well as your Q is equal to heat transfer 737.87. So how much amount of heat losses from the pipe that will be goes to heat gained by the fluid. Okay, that I am repeating Q is equal to mcp T naught minus Ti. That will be calculated your temperature rise T naught minus Ti. So now we move on to problem number 3.13. So initially water at 30 degrees Celsius enters a pipe 25 mm internal diameter with a mean velocity is given 0.06 meter per second. The pipe surface temperature is to be 50 degrees Celsius. Determine the outlet temperature for a length of 1 meter. Again, it is to be considered a pipe. The flow through the pipe. The pipe having internal diameter is given. Then length of the pipe is to be 1 meter. So initial temp, the water at initially 30 degrees Celsius. T I is given. Initial temperature of water is to be 30 degrees Celsius. The wall surface is maintained at a constant wall temperature. TW is given at 50 degrees Celsius. Okay. Our question is determine the outlet temperature of the fluid. This outlet temperature of the fluid is to be TO. It will be outlet temperature of the fluid. Right now it will be unknown value. Okay. Then initially we have to take properties of fluid at a bulk mean temperature only. In this case, we can't able to find out bulk mean temperature because we know only inlet fluid temperature only is known value. TO is to be outlet fluid temperature is unknown. That's why we can't able to predict take properties at your bulk mean temperature. Initially, we have to consider the properties of fluid at the inlet temperature. Then later we want to move on to your bulk mean temperature. So initially the bulk temperature is not known, therefore the properties value are taken at the entry temperature is to be considered. The inlet temperature of the fluid is to be 30 degrees Celsius. So I'm the properties, your density is equal to 997.5 kg per meter cube. Then your kinematic viscosity 0.8315 into 10 power minus 6 meters square by second. Your Prandtl number is equal to 5.68. Cp specific heat 4178 joule per kg Kelvin. Then K is equal to 0.6129 watt per meter Kelvin. So all the properties values from your data book. It is available page number 1 to 33. So water, here working fluid is a water. Therefore we have to take properties of water at 30 degree Celsius. Once we took the property, then we have to find out Reynolds number. Based on the Reynolds number only, we can able to identify which type of. Therefore, I am using the Reynolds formula. Reynolds number is equal to UD divided by kinematic viscosity. Then U is a 0.06 into your diameter will be 0.025 divided by your kinematic viscosity equal to 0.8315 into 10 power minus 6. Where just to find out this Reynolds number is equal to 1804. It will be less than 2300. Therefore, the flow is to be laminar flow. The flow is to be a laminar flow. So in this case, they did not mention anything. Therefore, I am assuming the flow is to be a fully developed hydrodynamic layer. So the flow is to be laminar. Then we have to find out that it is a 0.3 find out your x by d Reynolds number Prandtl number value is a 0.004 is to be less than 0.0001. Therefore, we have to use this relation. Nusselt number is equal to 1.67 into Reynolds number into Prandtl number d by x 0.333. So 1.67 your Reynolds number we already find out 1804, your Prandtl number 5.68, then d by x, your diameter of the pipe is to be 25 millimeter, then we are 0.025 divided by length of the tube is 1 meter. We are assuming we are getting Nusselt number is equal to 10.6. So Nusselt number is equal to Ht by K. Then from that relation, we find out the convective heat transfer coefficient. H is equal to Nusselt number into K divided by D. We are getting your convective heat transfer coefficient is equal to 260 watt per meter square Kelvin. Okay. So we just to look at this case, we already discussed. So if the duct is or pipe is maintained at a constant wall temperature, it is maintained at a constant wall temperature TW. Okay. Then this fluid having inlet temperature Ti, then it will be outlet temperatures to be Qo. Okay. Then the wall surface is maintained at a constant wall temperature. Therefore, the Tw is to be is constant value for their entire length of the flow passage. Okay. Then, if initially we have the fluid temperature Ti, while it flow through the pipe, it will be heated to outlet temperature. Therefore, it will be initially it will be having some temperature Ti. Then it will flow through the pipe. It will be heated up. Okay, that is it will heat it up to this one, but it is less than Tw. It cannot be exceed more than Tw because the heat is transferred from your wall temperature to your fluid temperature. Fluid. Okay, therefore this is called as your outlet condition. I consider say theta 2. Is theta 2 is the temperature difference Tw minus T Tw Tw minus the outlet temperature. These were inlet temperature difference is called as I consider say theta 1. Then Tw minus of your Ti, that will be your inlet temperature difference. Anyway, while calculating how much amount of heat transfer in this case, we have to using a bulk mean temperature, but it is not give your exact value because the temperature is keep on. Therefore, we have to take the logarithmic mean temperature should be used to find out your heat flow equations. In previous case also we used this relation. So that relation is nothing but your Q is equal to what is how much amount of heat converted from this surface to this fluid means we are using this formula. Q is equal to what is the formula we are using? HA into TW minus TB we are using. Here TB we are taking is nothing but these were average temperature of the TB is a bulk mean temperature. It is the average temperature of inlet fluid temperature as well as your fluid temperature. If it is varying linearly, then this expression is suitable. But is here this will be suddenly it will be increases after that it will maintain a constant. Okay, and it is a fully developed hydrodynamic layer at the entering region. Then it is varying gradually increases. Okay, after certain cases only we are touching. While using this zone, then we have to consider say your TB is a Ti plus Tmo by 2. Maybe this zone. This zone after this zone, we can use this relation TB is equal to Ti plus Tmo by 2. But in this entire region, it will be depends upon your logarithmic mean temperature. Therefore, this expression is not suitable for these cases. Therefore, your Q that can be calculated Q is equal to HA into your theta m. this theta m is called as your logarithmic mean temperature. This logarithmic mean temperature theta m is equal to, what is the formula? Inlet temperature difference is Tw minus Ti. That means theta 1 minus theta 2 divided by ln of theta 1 divided by theta 2. We can use this expression for your while calculating your heat transfer. How much amount of heat converted from the surface to fluid? We can use this relation in previous case. That case we are HA into TW minus T in B. But most of the situation we are assuming this to be where the inlet fluid temperature is difference is varies continuously. Therefore, you have to take your logarithmic mean temperature of your entire flow. Therefore, your Q is equal to HA. This temperature difference I mentioned is a logarithmic mean temperature difference, theta m. That the formula is LMTD is equal to logarithmic mean temperature difference equal to theta 1 minus theta 2 divided by ln of theta 1 divided by theta 2. Okay. So from that we know that Q is equal to how much amount of heat converted from the surface to fluid, that must be equal to heat gained by the fluid. So heat gained by the fluid is to be formula is mCp into outlet temperature of the fluid minus inlet temperature of your fluid. mCp T0 minus Ti. I am equating these two equations. So HA into logarithmic temperature T0 minus Ti. So it is nothing but this Tw, then this Tw will be cancelled. Then we are getting T0 minus Ti ln of Tw minus Ti divided by Tw minus T0 equal to mCp T0 minus Ti. So in this equation also we this T0 minus Ti, this will be cancelled. Therefore HA divided by ln of Tw minus Ti divided by Tw minus T was equal to mCp. Okay. So from that relation we find out Q is equal to HA into this will be cancelled. Okay. Then if we cross multiply along this equation, we are getting HA by mCp is equal to ln of Tw minus Ti divided by Tw minus T0. Okay. Here I am using minus symbol. How can you get minus symbol? Means if the heat loss from the pipe is must be equal to heat gained by the fluid. Therefore, the heat loss way I indicate here minus sign. Okay. Then if you cross multiply this side, then I am taking e power e ln will be cancelled. Okay. Then Tw minus Ti divided by Tw minus Tu is equal to e power minus Ha by mc, where m is called as your mass flow rate. Mass flow rate that can be calculated from rho a velocity, rho into a into velocity. Okay. This quantity I calculate. See H is contact area, how much amount of contact area the fluid is contact with your surface. Okay, that how much amount of heat transfer takes place, that will be your contact area or surface area for pi d into L divided by, while calculating mass flow rate we have to take a cross sectional area of your fluid passes through the passage. Therefore m is equal to rho AC, rho is to be 97.5 into area. This will be area. This will be your specific heat CP wells. Okay. Then this area is to be L. In this case, area pi by 4 d square. From that we find out HA by MC 0.664. I am applying here. We find out your outlet temperature of your fluid. TO is equal to 33.07 degree Celsius. So now we move on to problem number 3.14. A engine oil enters at initially 35 degrees Celsius into a tube of 10 mm internal diameter. At the rate, mass flow rate is given 0.05 kg per second and is to be heated to 45 degrees Celsius. Okay. Then tube wall is maintained at a 100 degrees Celsius by condensing steam. Determine the length of the tube is required. Okay, the question is how much length is required to transfer the heat. So your property should be evaluated to bulk mean temperature. Here the working fluid is to be engine oil. The oil inlet temperature is 35 degrees Celsius, where it's to be outlet temperature is 45 degrees Celsius. Therefore, Ti plus To divided by 2, we are getting 40 degrees Celsius. Therefore, you go to data book and refer oil 40 degrees Celsius. I took the properties. The properties of oil at 40 degrees Celsius density is equal to 876 kg per meter cube. Your CP specific heat 1964 joule per kg Kelvin. Your dynamic viscosity mu is equal to 0.212 Newton second per meter square. Then your K thermal conductivity is given 0.114 bar per meter Kelvin. The Prandtl number is to be 2870. This is a higher Prandtl number. So Reynolds number is equal to U kinematic. Okay. So if we here the problem we have only dynamic viscosity, and then we know this formula kinematic viscosity is equal to mu by rho. Okay, this formula is there. I'm applying here this kinematic viscosity. I replace mu by rho, that will be rho ud divided by mu. Rho is also density is known, but in this case velocity is not given, but the mass flow rate is given 0.05 kg per second. You know the formula m dot equal to mass flow rate equal to rho a u, velocity of the flow, average velocity of the flow. Then u is equal to m divided by rho a. While using this mass flow rate, we have to take areas to be a cross sectional area. Therefore, m dot is given 0.05 divided by density of the oil is to be 876 into pi by 4, diameter 0.01, 10 millimeter, it is converted to meter, 0.01 whole square. From that I find out velocity. U is equal to 0.7267 meter per second. Okay, once if you know the velocity, then we can apply this formula. We have to find out your Reynolds number. Okay, Reynolds number is equal to 876 into 0.7267 into 0.01 divided by 0.210. That will be simply we have to substitute all the quantities, your density and velocity and diameter divided by your kinematic or dynamic viscosity. From that I find out Nuzler, your Reynolds number is to be a 30.32 is less than 2300. Therefore the flow is to be a laminar flow. So the is not given, so we are assuming the flow is to be a laminar flow. So I am using this is a fully developed thermal area. In this concept, I am using the Nuzlet number is equal to the formula is 3.6. This is available in your data book. So initially we are assuming fully developed thermal layer. So what are the assumption you made? You just write down here. Made any assumption? You just write down, and that after that you take formula. So in this case, we are assuming, I am assuming laminar flow, fully developed thermal layer. The Nuzlet number is to be 3.66, where it is a constant wall temperature, as well as your length is much more greater than your diameter. Okay. So assuming the length is to be a long tube, because this initially the length is unknown. We are assuming the length is to be a long tube, as well as it is much more greater than your internal diameter. So your Nuzlet number formula is 3.66. So once we take from this formula from your data book, okay. The what are the assumptions made here? It is a fully developed thermal boundary layer for flow is to be a laminar flow. Number is equal to 0.66. So I am using this relation to find out your convective heat transfer coefficient. H is equal to your Nuzlet number 3.66 into your thermal conductivity K value 0.144 divided by your diameter is 0.01. We find out 52.7 watt per meter square Kelvin. But our question is to determine the length of the tube. So if you find out your length of the tube means first we have to find out your heat transfer. Okay, how much amount of heat transfer from your pipe to fluid, that is the convective heat transfer. Then we can use this formula, Q is equal to, what is the formula, M. This is also one formula. If it is a convective heat transfer question, we are using Q is equal to HA into M. This is called as your logarithm mean temperature difference, because the fluid is passes through the passage of pipes. It will keep on varies because it is heated from your heat is transferred from your pipe to fluid. That is it will gradually varying. Okay. Therefore, we are you take your logarithmic mean temperature difference. This must be equal to the heat gained by the fluid. The heat gained by the fluid we can be calculate M into mass flow rate of the fluid, then specific heat of the fluid Cp into your outlet temperature minus your inlet temperature. Okay, so I am using this relation. We find out your determine the length of the tube. How can you find out length of the tube? Once if you know the Q, then Q is equal to, in this case, your inlet fluid temperature as well as outlet fluid temperature is known. Therefore I am using this relation. Q is equal to mcp T naught minus Ti. From that I find out Q. Then once you know the Q is equal to HA into theta m. Theta m is the logarithmic mean temperature difference. So first find out heat transfer. Q is equal to HA LMTD, logarithmic mean temperature difference, equal to mcp T naught minus Ti. So first of all, I am using this relation. We find out your Q value. Q is equal to your mass flow rate 0.05 into Cp value 1966, in the outlet temperature of the oil is to be 40 minus inlet temperature 35. We are getting 983 watt. Okay, here, so the wall is maintained at constant wall temperature. The fluid having initial temperature Ti, that will be passes through the pipe. It will be heated up. Okay, here the heat is transferred from surface to your fluid. This will be inlet temperature. It will be your outlet temperature of the fluid. The temperature difference between these two is called as your outlet. I am considering say theta 2. If I am considering the inlet wall temperature, or wall temperature is a constant everywhere. That's why it is a TW. The temperature difference between inlet condition, that will be your theta 1. So your logarithmic mean temperature LMTD, logarithmic mean temperature difference, LMTD formula is nothing but your inlet temperature difference of theta 1 minus theta 2 divided by ln of theta 1 divided by theta 2, where theta 1 is nothing but Tw minus Ti, where theta 2 is nothing but this also is maintained a constant Tw T outlet temperature. So this flow will be varying, the temperature is varying when it is flow through the pipes, so gradually increasing. Therefore, I am in order to take a average temperature, I am to calculate your logarithmic mean temperature difference. So if we find out LMTD, the wall temperature also known value, inlet temperature of fluid, outlet temperature of fluid, all are known value. We find out LMTD value. So then we use this, from this equation we find out Q, then Q is equal to HA into your LMTD value 59.9 degrees Celsius. Okay, then your Q is equal to 983 is equal to your convective heat transfer coefficient. We already find out area. The contact area is to be pi dl. This length of the tube is unknown into 59.9, and from that I find out your length of the tube is equal to 9.92 meters. Okay. So then problem number 3.15. So this problem is to be water is to be heated at the rate of 0.01 kg per second. So here what is heated at the rate of mass flow rate is given from a bulk temperature of 20 degrees Celsius to 60 degrees Celsius as it is flow through the tube of 20 millimeter internal diameter by means of electrical resistance heating at the rate of 55 into 10 power 3 watt per meter square. Calculate length record. Also find the heat transfer coefficient. So it is also an important situation here. So if it is said that this we are using heated by your electrical resistance, that means continuously subject to constant heat flux because the surface is subject to constant heat flux. Okay, because it is like continuously heated. That heat flux is given. Okay, that is to be a flow through the pipes. Inlet fluid temperature is 20 degrees Celsius to 60 degrees Celsius. The initial temperature Ti is given 20 degrees Celsius. Your outlet temperature of fluid also is given 60 TO is equal to 60 degrees Celsius. Okay. Then again we have to find out the properties at the bulk mean temperature. TB is equal to your inlet plus outlet plus inlet plus temperature divided by 2. We are getting 40 degrees Celsius. So here working fluid is to water. Therefore the properties are valued to 40 degrees Celsius. We find out density rho is equal to 995 kg per meter cube. Your kinematic viscosity is equal to 0.657 into 10 power minus 6 meters per second. Your Prandtl number 4.34. Then your specific heat Cp is equal to 4178 joule per kg Kelvin. Then K is equal to 0.628 watt per meter Kelvin. So from that I first find out the Reynolds number. So your Reynolds number is equal to UD divided by your kinematic viscosity. Then velocity of the flow is given. So here velocity of the flow is not given, but the mass flow rate is given. Therefore, from that we find out your velocity. Mass flow rate is m dot equal to rho a u, where u is called as average velocity of the flow. Then u equal to mass flow rate divided by rho a, and your mass flow rate is given 0.01 divided by your density of the fluid at 40 degrees Celsius 995 kg per meter cube. While calculating your mass flow rate, we have to use your cross-sectional area. Because the fluid passes through this cross-sectional area, we have to use pi by 4 into d square, where diameter is 0.02 square. Okay, because it is a 20 mm internal diameter. So once if you know the velocity, then we have to find out your Reynolds number. So Reynolds number is equal to UD divided by kinematic viscosity. It is to be less than 2300. Therefore, the flow is to be a which flow? Laminar flow. Then it is a laminar flow, but we are subject to constant heat flux. It's a laminar flow and it is subject to a constant heat flux. Okay. So we just look at here. I would like to draw one. So if this case is like previous case, so because we are continuously supplying the heat, okay, therefore your wall temperature or surface temperature of the pipe, it will be keep on increasing. It is a function of your distance. Okay, these were distance or length of the pipe. So if you are continuously given your constant heat flux to the surface temperature in this location may be TW1. This location it may be TW2, where TW2 is greater than TW1. Okay, so the surface temperature is to be a not a constant here. It is because we are continuously given heat flux to the system. So your wall temperature is increasing, but your fluid also initially the fluid having initial temperature Ti while it is flowing through the pipe. Initially it is heated up. Okay, then we are giving constant heat flux or constant heat flux to the fluid. Therefore, this temperature will be varying linearly, inlet to outlet temperature. Therefore, initially it has a certain temperature, maybe it is have initial temperature here, or maybe it have initial temperature. It will be gradually varying, linearly varying. Why it is linearly varying means it will be because we are giving constant heat flux to the system. So if we given constant heat flux to the system, okay, but every certain time interval we are giving constant heat flux to that, the fluid is heated at a or very linearly. Okay, therefore it is for inlet temperature Ti, it is for outlet temperature To, because it is varies linearly. Ti. Okay. Then if you here it is a initial temperature will be certain temperature, it will flow along to the pipe. So if you have initial temperature Ti, maybe it is a 30 degrees Celsius. After certain location, it is a 30 degrees Celsius. After certain location, it is to be a 40 degrees Celsius, 45 degrees Celsius. And then it will comes to certain outlet temperature will be higher than the your inlet temperature. Initially, it will goes and heated up. Therefore, in this case, the heat is transferred from wall to your fluid. We are substitute constant heat flux. So, initial air TW the wall temperature to your fluid temperature is initial difference is high. Later, it will comes to linearly. So, the wall temperature also initially having higher value after certain interval. So, then it will achieve linearly from up to this location. After that, the flow is to be fully developed flow because this temperature difference between your wall as well your bulk mean temperature is your wall temperature is keep on increasing. That will be your outlet temperature, the Ti. So while they consider a fully developed flow, your heat transfer, we can use this formula. Heat transfer Q is equal to what is heat convective heat transfer coefficient H A into here TW wall temperature minus your TB, where TB is nothing but your bulk average temperature of your inlet temperature plus your outlet temperature of the fluid. It will be a bulk temperature TB, the difference. So here this difference will be linearly because these two lines are parallel line. Therefore, we can use this relation HA into TW minus TB. Okay. So in previous case, you see that in this case, the wall is maintained at a constant wall temperature. The temperature is variable from inlet to outlet. It is gradually increasing, but wall is maintained. So every location we can't these lines to be not a parallel. So therefore it will vary linearly. Okay. So that's why I am taking to find out your logarithmic mean temperature difference. But this case, these two lines to be a parallel line. Therefore, we have to take your temperature difference of your wall temperature to your bulk mean temperature while calculating your heat flow equation. Okay. Then we are assuming the flow is to be a laminar flow. It is subject to a constant heat flux, and also we are assuming fully developed flow. Then you took formula Nusselt number is equal to 4.364. Once if you know the Nusselt number, then Nusselt number, this formula is available in your data book. So it is pipe is subject to constant heat flux. It is a flow through the pipe. It is a laminar flow. Then your Nusselt number is equal to 4.364. Okay, then Nusselt number formula is HD by K. Then HD by K is equal to 4.364. From that, I find out your convective heat transfer coefficient 136 watt per meter square Kelvin. Then I am using energy balance equation that your heat flux. This problem heat flux is given. Heat flux is nothing but your heat transfer per unit area is called as your heat flux. Heat flux is to be one. I think the heat flux is given. What is for heat flux? 15 into 10 power 3 watt per meter square. This a small q value is given. This small q your heat transfer q is equal to
your heat flux into area. That means Q into your area. Area has to be pi dl is equal to how much amount of heat losses from the pipe must be equal to heat gained by the fluid. To be this a pipe. So the heat is transferred from convective heat transfer from your pipe to this fluid, where air fluid is passing through the pipe. So while the heat transfer from this pipe to fluid, that's why the fluid will be heated up. Okay. Therefore, this inlet temperature Ti, how much amount of heat losses from the pipe must be equal to your heat gained by the fluid. That's why I'm using energy balance. Heat losses from the pipe must be equal to heat gained by the fluid. MCP T0 minus Ti. From that, we find out length of the tube, how much amount of length is required to transfer the heat. Okay, L is equal to MCP T0 minus Ti divided by Q into pi d. Your heat flux is given 15 into 10 power 3 watt per meter square. Inlet molecular outlet temperature 60 degrees Celsius minus inlet temperature 20 degrees Celsius. If you substitute, we find out the length of the tube L is equal to 1.773 meter. Okay, that is a in previous problem. This problem, the slight difference is only while calculating your heat. In this case, we can use the Q is equal to HA into TW minus TB. Suppose if it is maintained a constant wall temperature, means the temperature from inlet to its outlet is varying, difference is significantly varying. That's why I am taking logarithmic mean temperature difference instead of TW minus TB. In this case, this fluid will be having subject to constant heat flux. Therefore, the fluid gets heated up. Inlet to outlet temperature is to be varying linearly. That's why I'm making a straight line. Okay, then it will be continuously the surface subject to a constant heat flux. Therefore, each and every location, your wall temperature also function of length of the flow. Therefore, your TW and TW2 is will be keep on increasing. That's why it will keep on increasing. After it will reach constant. This line is parallel to this line. Up to this location is to be called as this. After this region is called as a fully developed flow. Fully developed flow. So if it is fully developed flow means we have to take your while calculating heat flow rate, Q is equal to HA into a temperature difference TW minus your TB. TB is nothing but your bulk mean temperature. This is nothing but your TI plus TO divided by 2. Okay. That in this case, this inlet to outlet temperature is to be not to be linearly. It is a difference is significantly increases. That's why I'm taking your while calculating LMTD, the temperature difference. So I'm taking logarithmic mean temperature difference. LMTD is equal to theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Okay, where theta 1 is nothing but inlet temperature difference of your pipe wall temperature to your inlet feed temperature. Theta 2 is nothing but your temperature difference of wall surface temperature to your outlet feed temperature. Okay. So whenever if you have any type of problem, it is a flow through the pipe. Therefore, we have to find, we just to go to your internal flow in your data book. Then next we have to find out this type of flow. All properties would be taken from your bulk mean temperature. Okay, from the bulk mean temperature, we will take the properties from your data book. Then we have to find out Reynolds number. If the Reynolds number is less than 2300, then the flow is to be a laminar flow. Reynolds number is greater than 2300, then the flow is to be a turbulent flow. Maybe next class we will solve some numerical problem that will be related to your turbulent flow. So all these cases flow through the pipes, there are two concepts. One is to be a constant wall temperature. That means the surface of the temperature is to maintain constant entire flow through the pipe. Another one is the pipe is subject to constant heat flux. Okay. So based on that, we have to select the formula from your data.